Late. I didn't know that one of the responsibility of chairman was supposed to ring a bell. I thought somebody was doing for me, but so sorry for starting a little bit late. So the first speaker, Paul Durbin, for some reason listed as R. Durbin, but most of us know him as Paul Durbin. Boundary layer transition by discrete and continuous mode.
The work I'm going to present was done by, from the PhD thesis by Yang, and there were major contributions from Tamarzaki. And despite his a more lucrative location, Yang was a PhD student at Stanford at the time he worked at In the literature, you see reference in the context of boundary layer transition to orderly transition and bypass transition. Oh, is there a switch on? The orderly transition and bypass transition. At the last of these workshops on turbulence 9 years ago, Neil Sandham made the comment to me that when people asked what's bypassed, he said theory. So we have our own theory, and maybe other people have their theories, but our theory is pretty much classical, or Sommerfeld theory that orderly transition it corresponds to the Tolman-Schlichting wave by definition, or the discrete modes, and bypass transition is simply can be understood at least in terms of the continuous mode. So our theory is classical or Sommerfeld theory. Now I should say that I'm assuming this audience is pretty much orthogonal to the one at ETMM in June, and I'm presenting the same talk without apologies. The motivation for this work was actually a talk at the Minnebrook conference, which Radam Narasimha is involved in organizing. And what was asserted is that on compressor blades, transition, despite the high free stream turbulence, which is the condition for bypass transition, that on compressor blades, Tolman-Schlichting waves played a role. So there's a sense in which maybe it was a combination of discrete and continuous mode or orderly and bypass transition. That was the motivation. I'm not sure that the experimentalists who asserted that were correct, but that was the motivation for this work. So just to give some context, real world context to the extent that a DNS is the real world, this is what we're thinking of. Turbulence flowing over a surface, which in this case is a compressor blade. And what you see is on the lower side of the blade, which is the pressure side of the blade, you see what the characteristic features of bypass transition, continuous mode transition. These are long disturbances which then break down into turbulence. On the suction side, the upper side of the blade, you do see some upstream disturbances that are elongated. In this case, they're interacting with more of a Kelvin-Helmholtz instability. It's not the situation of interest or the speculation that we wanted to look into, but it is an interaction between free stream turbulence and an instability. So it provides some form of motivation. And this is what you see, these elongated disturbances upstream, which in this case are interacting with a Kelvin-Helmholtz and causing a highly three-dimensional breakdown and transition to turbulence. So this is the situation of interest, but it's Tolman-Schlichting waves, not Kelvin-Helmholtz. I should say this is a mildly separated flow, so it's not what we're looking at. But that is sort of the background, the motivation for the work. So the theory, as I said, is classical or Sommerfeld theory, or Sommerfeld equation represented symbolically here, the Squire equation, and then the coupling term where or Sommerfeld mode forces the Squire equation. The Tolman-Schlichting waves or discrete modes tend to zero at infinity. The continuous modes are bounded, in fact, oscillatory at large y. And so this is what is the starting point for normal or organized transition, and this is the starting point for bypass transition. Now, those elongated disturbances can be understood in the context of our Sommerfeld theory by noting that the continuous modes are just vortices. In the free stream, it's just vorticity that is convected along, and it just decays by viscosity. It's not an unstable disturbance. It just decays. However, that's true of horizontal vorticity and vertical vorticity. They both are convected along and decayed, so they have exactly the same dispersion relation, and this becomes a resonant forcing term, and you get linear growth. So the coupling between the free stream and disturbance and the boundary layer comes about through that, and it generates the long features. Okay, so these are what the continuous modes look like. And in the discussion, one of the discussion sessions yesterday afternoon, there was some talk about shear sheltering. Well, shear sheltering is due to the fact that the continuous modes look like area functions. They're oscillatory in the free stream and they decay in the boundary layer. And the result is that the lower frequency disturbances don't get into the boundary layer and they don't cause transition. But if you calculate the fairly low frequency modes, they do penetrate into the boundary layer. And so you get a low pass filtering. The shear, Joy and Hunt used the term shear sheltering, but actually in this context, it's low pass filtering. The shear acts like a low pass filtering because of the extent of that area function into the boundary layer. So that's what the continuous modes look like. They represent free stream turbulence. And then the discrete modes are Thome-Schlichting waves, which have a maximum inside the boundary layer. Let's see what. Okay, so let me review, and it is regrettable how quickly time passes, but this is actually something I presented at the last of these meetings, which is already 9 years ago. But this is our perspective review of continuous mode or bypass transition. And let me just put a correction here, since I believe Professor Moffat is there in the audience, that I actually learned this argument from Moffat in 1967. Javier cited a paper in 1974, but it is at least as old as, I shouldn't say as old, it at least dates back to, at least dates back, I learned it from Moffat's paper, and it also appeared in volume 1 of Annual Review of Fluid Mechanics, so it wasn't actually the algebraic instability literature, it was the rapid distortion literature. And rapid distortion theory explains why you can ignore dp by dx and come out with Prandtl's argument that velocity fluctuations are due to vertical displacements of mean momentum. The downward displacements cause high-speed regions, which in terms of velocity vectors look like jets in the positive direction. The upward motion produces negative velocity fluctuations, which look like negative jets. And that's near the wall. If you go to the upper part of the boundary layer, you just see the upward moving disturbances, which are long negative jets. And those turn out to be the origin of transition, at least in our computer simulations. So these jets, which are due to this displacement, this line of argument, these negative jets become unstable near the top of the boundary layer, break down, and at this stage, you're seeing a patch of turbulence filling the boundary layer. So experimentalists commonly are looking either at the wall or in a plane near the wall, and they see, if you look at the pictures, you see spots suddenly appear, apparently out of nowhere, but they do have an origin, but it happens to be higher up in the boundary layer. So the turbulent spots that seem to just appear next to the wall can be traced when you have a 3D DNS. Okay, so this is the review of continuous mode transition, and you see the same things on a compressor blade. So now the question which was motivated by that talk at the Minnowbrook workshop is, if you add Thome-Schlichting waves, do you get a transition mechanism which is a combination of discrete and continuous mode, or bypass and orderly transition? And you can answer it even before you do the simulation. You say, yes, the forward and backwards jets, you add a Thome-Schlichting wave, which is has horizontal vorticity, and it will get warped and undergo secondary instability. Unfortunately, that's sort of what happens. So you like your argument to be wrong, so you can learn something new. But it's a little bit more subtle, but that's the gist of the understanding. The continuous modes induce these jets, forward and backward jets, in the boundary layer, and those then can distort the Thome-Schlichting wave. Okay, so this is the computer simulation. We have an inlet plane here, which is downstream of the leading edge. The R theta is somewhere around 200 at the inlet. And we're calculating in a rectangular box. At the inflow, we have a Blasius boundary layer, add the continuous mode, which represents the free stream turbulence, and a discrete mode, which represents the boundary layer instability. And let's see, an unstable Thome-Schlichting wave was chosen for the discrete mode. And for the continuous mode, we choose a low enough frequency that it will penetrate the boundary layer. If we chose a higher frequency, it would be sheltered by the shear, but the lower frequency modes get into the boundary layer and create these jets. And I say streak equals jets. That's maybe a reference to the discussion yesterday, streaks is a general term. In this case, we mean those jets in velocity which will distort the Thomé-Schlichting wave. Okay, so we're looking laminar to turbulent transition. Oh, and I should say, the Thomé-Schlichting wave is two-dimensional. The continuous mode is three-dimensional. It has a span-wise wavelength which has to fit in our computational box. We saw two types of behavior which are epitomized by modes 2 and 5. The number of waves across the flow will be either 2 or 5. We did other cases, or I should say my student did other cases, but they fall into one category or the other. Okay, so first, just put in the Thomé-Schlichting wave alone, and of course it grows, doesn't do anything, doesn't produce turbulence. If you time average the skin friction, it follows the Blasius pretty closely. It's a mildly perturbed boundary layer in terms of the skin friction. I don't have the same plot for the continuous mode, but it's the same. It produces a disturbance, but the averaged effect is the skin friction isn't changed very much. For the continuous mode alone, I have just a looking down on the boundary layer contour plot of u velocity, showing in fact there is nonlinearity. The wavelength is dropping in half due to the quadratic nonlinearity. But this is the mode 2, two waves across the computational domain, five across, 2 and 5. And the mode 5, it decays more rapidly. So it's completely innocuous. It produces a disturbance, these jets, streaks, whatever you want to call them, but they don't transition. It's just an innocuous disturbance. And like I said, the skin friction wouldn't show anything. Here's a vertical section showing these jets. The negative jets are upward displacement, so they're moving upward, and the positive jets downward displacement, and they're closer to the surface. But now you put the two of them together, and that's all, just those two added together, and it breaks down into turbulence. So not unexpected, but it happens maybe more rapidly and more explosively than we might have anticipated, but we did anticipate that the jets would work the Thomé-Schlichting waves, and that's what happened. And now the skin friction, you can see it's not at all innocuous. It jumps up. This is the empirical turbulent level, and it jumps up to the turbulent level. And so you see it is transition. This is the Thomé-Schlichting wave alone, would not have transitioned. Okay, so this is showing how the transition location depends on amplitude, and this is the mode 2 behavior, this is the mode 5 behavior. With zero amplitude of the continuous mode, it would not transition. If you put in a small amplitude, it transitions here, increase the amplitude, and it moves upstream for the mode 2. For mode 5, it would not transition. You put in a small amplitude, it transitions over here. You increase the amplitude, and it delays transition. So you put in a stronger disturbance, and you get later transitions. So that's the difference between mode 2 and mode 5 type of behavior. See, there is not a particularly informative animation, but this is an animation of the mode 2 case, showing you can see now that what's happening. That you can see the Thomé-Schlichting waves getting warped by the jets and then breaking down into turbulence. See, and here's mode 5. In which the same thing is happening, but as I'll explain, it's not quite as simple because where you see the Thomé-Schlichting waves being warped, the wavelength is more than twice the spacing of those jets. It's actually being warped by a number of jets, and it's not quite as clear-cut as the jets just warping the Thomé-Schlichting waves, but it is breaking down by Thomé-Schlichting waves warping and evolving into turbulence, which I should say. You mean one here and here? Yeah, I think this is more lifting up from the wall, and then here is where it's actually becoming sustained turbulence. But it's a transition process. Okay, so here are some still pictures from an animation showing you. Now here you see this lambda-shaped structure, which in orderly transition you get Thomé-Schlichting waves, then lambda vortices, but this wavelength is about 1/10 of what you'd see in, say, an H-type secondary instability. So it's definitely being caused by the continuous mode jets. We did do a flow K analysis for what it's worth, take an ansatz consisting of jets and Thomé-Schlichting waves, periodic in Z and in X, And the flow K analysis does predict instability at the wavelength of the continuous mode. Well, let me just jump forward to draw the contrast. That for the mode 5, and this is our explanation, is that the instability from the flow K analysis is 2.5 times the wavelength of the continuous mode. So that's why they don't lock on. And whereas in mode 2, they lock on to the continuous mode wavelength. So the flow K analysis gives some rationale for that. So now, so you can see these are forming the lambda contours, and like in orderly transition, the lambdas develop and then break down into turbulence. And here's the lambdas. And here's, so in mode 5, you can see the wavelength of the jets produced by the continuous mode, and then these lambdas actually span several jets, and it's basically something like 2.5 of them. But you still see this lambda-shaped structure, which you would think is associated with lambda vortices forming and lifting up away from the wall and breaking down. Here's side views showing this is side view showing the way it lifts up away from the wall. These disturbances are lifted up away from the wall. Recently, Tamer generated some better graphics to show them lifting up. These are the Q contours. So these are the legs of the vortex. This is showing you in the free stream we actually have this decaying continuous mode, but it induces a highly nonlinear response inside the boundary layer. These vortices are breaking down, and in back of the screen you can see that the turbulence forming at the apex of the vortices. And here's the mode 5 case. Again, you can see here the jets now. The jets, and you can see the wavelength, the size of the lambda vortices is very different from the jets. So somehow or other they are producing this. And now you see the, where's your sign that says how many minutes?
I'm standing up 1 minute.
1 minute, there's, okay. 1 minute? Okay, so here, this is showing the lambda vortices, and here they're breaking down. So since there's 1 minute, I will, and here, so here's the mode 2 case, mode 5 case, just filling in those velocity vectors, showing that it really is a horseshoe vortex lifting away from the wall and becoming unstable at its apex and breaking down, just as in secondary Thomson-Schlichting wave instability. And so I guess this is the last result I'll show you. This is the sort of explanation for the why mode 2 seems to delay higher amplitude delays transition. This is what the Thomson-Schlichting wave would do by itself. When you put in the continuous mode, it's well known that suppresses the growth of Thomson-Schlichting waves. It's not contributing to Thomson-Schlichting waves. It actually suppresses the growth rate. And we see that, and this is a spectrum to show that it actually gets suppressed. In this case, you see the subharmonic growing, and there seems to be an instability that involves the subharmonic growing, whereas the harmonic actually is not very much affected by the interaction. So it suppresses this, but causes a secondary instability. And where transition takes place is a competition between this being suppressed, the Thomson-Schlichting wave growth being suppressed, and the secondary instability taking over. So if the continuous mode is very strong, it will kill off the Thomson-Schlichting wave, and you won't get transition, or it will delay transition. And that seems to be the explanation for what happens in the case of mode 5. It suppresses the growth of Thomson-Schlichting waves, and the secondary instability actually is not very strong. And so if you put too much of an amplitude, it's not killing them off, but it's delaying the growth of the Thomson-Schlichting wave, and you increase the amplitude and transition moves downstream because of this effect of suppressing the growth of the Thomson-Schlichting wave. Okay, so conclusion then, hopefully on time, that the interaction does take place. It occurs via lambda patterns. The mechanism, which I just mentioned briefly, is the stabilizing effect, suppressing the Thomson-Schlichting wave, but inducing secondary instability. And the competition between those two effects explains the difference between mode 5 and mode 2.
I have the privilege of asking the first question, Mr. Chair. So, quote unquote, the bypass transition also takes place in the channel where you don't have a continuous mode. So how do you explain that?
Well, the term bypass is non-specific. It says what's not happening. You're not doing something. You're bypassing something. So I should say transition beneath vortical disturbances, beneath free stream turbulence is the type of...
But channel, you don't have a continuous mode. So it's everything's in discrete mode.
Yeah, but sometimes in channel flow, what you're actually referring to is subcritical transition. So I don't know what the connection is between bypass transition in a boundary layer beneath free stream turbulence and the bypass. You see, I haven't really looked at that subject, but I know the term bypass is used in many contexts.
Any other question?
This damping of the TS waves by the streaks, I guess that's similar to what Kosu Brown.
Exactly.
So did you compare with them? Did you find the same?
Yes, we did the
Essentially the same thing, I guess. Right?
Yes, we did flow analysis and first tested to make sure we were reproducing the results, and we see the Tolman-Schlichting wave being suppressed, so we agree with 100% with that effect. But then there's a secondary instability, which is once you put in the Tolman-Schlichting wave, it will be warped by the free stream turbulence, and it's a competition between those effects, but we agree 100% that effect occurs, and that's why mode 5 behaves the way it does.
One more quick question.
On the mode 2 transitions you had, was one of them always occurring earlier in one half of the width of the wave than in the other?
It's a little bit
Breakdown,
complicated because
breakdown.
there's a sinusoidal variation across the stream and it's not steady. So the position of the pilot, it's actually, the inlet disturbance has a low frequency.
Yeah, that's what I wondered.
So it will move from one side to the, those do move from one side to the other. I showed you mostly the case where it's on this side, but if you wait later, it will be on the other side of the channel, of the boundary layer.
Okay, we'll move on to the second question. I'm a second speaker.